Sorry, I'm a little late. This is kind of weird. I left that there accidentally. So the homework, like the grads did great on it, and both of them are like really excellent, you know. The undergrads, like not so much, but they did okay. So it's a pretty good job on that. The that derivation, that it's a mess. Like, all right, so both of you effectively did the derivation, you know, but the logic behind it, I still don't exactly get. Like, it's kind of this Sue and Wei thing. He mentions other people too, like other papers that have to do with it. But somehow you need to get to like this kind of equation. So, I mean, I don't know, it seems to be like once you get to that equation, then you can pretty easily kind of get the this power dependence, the Krieger equation. But the first step seems to be pretty odd to me. Like he says at high concentration, so you have the Einstein equation somewhere. This one, and he says at high concentration, he's going to have this viscosity plus a change in viscosity, and that's going to be related to this same equation, but with a delta concentration in it, and then plus the original plus this viscosity, and then anyway, if you accept that idea, then you can get to that derivative equation, and then you can, once you get the derivative equation, you can do the integral. It still seems a little dicey, and also like if you get the final equation that you get from it, and you try to get back to the, so you know the Einstein should work at the low concentration. So let's see, where is the Krieger one? So the whole thing is that he's trying to get high concentration. I think that the Krieger equation kind of goes back to the Einstein when you say it's dilute. So, okay. So wherever it is here, Krieger's in here somewhere. Anyway, so it doesn't exactly, like the Krieger will go back to the Einstein if you put in dilute. So it kind of looks like, anyway, I'm not sure it really describes concentrated. That's the bottom line. It explains the data, like it fits the data, but it seems to be still like an empirical function. Derivation isn't that convincing. It's a possible way to get it, but I don't know, any comments on that thing? It's kind of dry, you know, I mean, but basically I thought it seems like a function that you need to know, and I hadn't seen it before. I saw it there, so that was kind of important. Then, oh, you guys did really well on that homework, I thought so. Except the undergrads kind of, it was kind of typical. It was okay what the undergrads did, but it was like compared to the grads spent a lot of time, it looked like, doing it, like deriving that thing, and also the answers to the different models for rotation was very impressive. I mean, it really went through the data, through the papers and things. Anyway, so I wanted to finish this stuff and then maybe go through an example, and then And then Friday, I'm not going to be here, so I'll just do a Zoom class. And then it'll be like a homework on a polymer thing, like maybe a nanocomposite. Like next week, I'd like to go through a little bit of nanocomposites. So then, yeah, so then it'll be like, we'll just have everyone does their own last homework, you know, and it'll be due like end of finals week. So maybe it's something on, I don't know, the class is supposed to be for like materials grad students. There's only one materials grad student in here. So, but like the qualifier, there's a section on polymer physics. So it's usually the last quiz I do something like an old qualifier question. So it might not necessarily be about polymer nanocomposites. So it'd be just like a practice qualifier question thing, for which I think you give them like 2 hours to do it or something like that. So you kind of put that timing on if you wanted, if you're the one materials grad student in here. You know, so otherwise you can do whatever you want. But anyway, so last time I kind of went through a little bit of this. I mean, I mentioned that there's this business analytics thing. It's weird, this machine learning, this whole thing, it seems like there's kind of two groups of people. One group thinks it's the greatest thing, and I think half the people think it's kind of like nothing, you know, like not like something that's been around a long time and not exactly really that important. So
reality, it's probably somewhere in between.
I don't know. I'm still out, you know, but I have to tell you, this is the first time I really looked at it seriously. And I was writing a proposal, not on polymers, but on like doing agriculture stuff. So it was kind of a weird thing, but basically with Africa, the idea was like get the sensors, then get the internet of the weather and everything and predict for growing crops. You know, so, but looking at it, you know, whether that would be viable or not is kind of like pretty questionable. So, and it also like maybe just simple things are more important than trying to do such a complicated thing. Nonetheless, like people, especially people that are at measurement labs, like at the synchrotron and the neutron facilities, and then NIST is a standards lab. And people at the Air Force, so the government agencies are really hot on this because they get a lot of data. Like say you're in the Air Force and you get a lot of data coming in about someone attacking or whatever in the chemical agent. So DARPA's, like I worked on a DARPA project that was like a wristwatch that would send back a signal when everyone gets exposed to nerve agents. I'm not proud of it, you know, but basically it was a James Bond kind of thing. You strap this on every soldier, and then the general would be sitting back and have a screen that'd be like popping up red. You'd say like run away from that type thing, you know. So I don't think it ever reached quite that point, but this was a while ago. Anyway, you can see how machine learning would be pretty useful in that scenario, because you could say like, kind of have the computer figure out where you should run to. So the military's interested in it, and these measurement labs are interested because they're trying to do, their argument is we need more money because we can do it faster. Like we can do this whatever diffraction measurement say. We can do it like instead of taking 15 minutes, we can do it in a millisecond. So then they need like in situ measurements to look at, like watch the thing during the time of its progression, you know, so you can map it out. Or the other alternative is you have every possible combination of everything on one plate, and then you just zap, 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 zap. And that exists for protein crystallography. So you have like, you have to crystallize, when you want to make a new drug, and that's going to be a targeted protein, and then you have to crystallize it to get the structure. So then you're going to have this, you can watch the growth of the crystals, or you can make like a whole series of these crystals, and then just, you're going to be in the exposure time again, is like 10 milliseconds. because the one thing, the protein burns in the bean. So you only have 10 milliseconds to look at it. The X-rays destroy it. And another is like the flux is so high that they've gotten this down to being so fast. So anyway, so they have robotic testing where they'll test like 100,000 samples in a day or something. Right, because otherwise it's a waste of money to have someone measure 10 milliseconds if you have to have a guy walk in with a sample every time, right? So you have them set up a rack of 10,000 samples in Connecticut and ship it to Chicago, strap it onto a machine, everything's preset, push the button and it does the 10,000 whatever samples in one day. It just runs on that, a robot does it. Everyone's trying to get that kind of operation going. But everything you do isn't going to be like that kind of measurement, you know, like there's only certain things, compounding, or like when they develop this room temperature or high temperature superconductors, then you have possible oxide components of maybe 50, you know, and then you have to mix and match all of those at all different compositions. So literally you're going to have millions of samples, right? And so you can run through that kind of sample set with an automated robotic machine. Then you could possibly find the solution to the compounding. It's basically a compounding problem. So for those things, it makes sense, but those are pretty boring things to do. Like those aren't really, and they aren't even really science, you know, they're more like just a lab technician. So setting that whole operation up, it's a lot of pre-measurement effort. So anyway, it's kind of hard to tell if that's going to be worth it or not. I mean, in the sense of funding, like from my perspective, you need to get money. So if you sense of funding, people are really happy to fund it. So, and you can basically fit this into anything you're doing. So if you're going to be begging for money, it's kind of useful to say that you're doing this high-tech robotic whatever, and then the thing decides and it spits out the answer. If you can convince people that that's true. So part of it is just convincing people it's true, and then the other part is finding people to do it, because it's going to be kind of boring. Basically, it's going to be a lot of setting up programs and things, right? So that's not necessarily the most exciting thing to do. On the other hand, those people are guaranteed jobs because it's a feedback cycle. So it's eating on itself. The more people doing it, the more want to do it. And the more to administrators, it looks like a good idea. Like it looks like you can save somehow doing this. So so that's the reasoning. It seems like kind of an odd reasoning, you know, to go to do. So it kind of has nothing to do with science. In fact, you know, like it seems to be anti-science in a lot of ways. So, but nonetheless, like the majority, like half the money for science is going into this area, like something like half, a big chunk, especially in the military and things. So everyone is signed on. These are all the players in science in the US, and they're all signed on, and they all get the president to put into his budget a line item for, you know, $1.5 billion, which is a lot of money. So that's a sizable chunk of the entire US research budget, right? So maybe it's like 10% of it or something. So anyway, so that's kind of where this is. So it seems like it's worth mentioning. Also, if you go to meetings, like it's going to be that there's people doing this. And then it's kind of interesting. Like it's kind of easy to do, and if you're like a computer nerd kind of person, then it's kind of easy to write the code for it. So there's all this freeware out there to do it. So you can do it, basically do it without paying for anything with your laptop. You know, you can use like Google. If you have so much data and you have to crunch the numbers, you can use the Google has like a free website for doing kind of upload the Python code and it just runs it for you on your data sets up to a certain point, and then they start charging. So it's the same kind of thing. Like you get used to using Gmail, and then all of a sudden you have to pay like $10 a month You know, I mean, because all your mail is on it, and transporting it over is going to be too big of a pain in the neck. So it's the same thing with this. Like you get used to using this Google, forget the name of it, their website in Iowa. So anyway, kind of went through this stuff. So this is the thing to go through. This is from this paper. This is from this machine learning for dielectrics, which they go through. The nice thing about it is they tell you exactly how to do it. Like they give you all the programs to do each step of the thing. So, but this is only one. This is like a design for design of materials. There's a bunch of different tasks that you can do, and some of them listed here. But basically, you can just use machine learning to kind of categorize things that are happening. Like you have a huge amount of data and you want to say, break it into categories. You know, so you have like the red type and the blue type and the green type, and like how the thing breaks apart. So you can use it to do that, to analyze huge data sets, break it into pieces. He's looking at it, in this case, kind of prescriptive, I guess, like predictive and prescriptive. So not descriptive, not diagnostic, but basically like he's going to take that data and try to say, like, make a new thing with it. So that's like 3 and 4, like more or less the higher level of this game. There are these other areas though. So anyway, he's gonna say, I want to make a super dielectric material. So it's gonna have a dielectric constant and it can't have a dielectric breakdown, which means like if you put in a high enough voltage on anything, it'll arc across it, right? So you have to, and then it'll heat up in that case. You need to know thermal behavior too. So it has to have good thermal behavior, and it has to have a high dielectric constant, and it has to have no breakdown. And then it also has to, the dielectric constant is frequency dependent. So you have to have a certain spectrum for whatever application you're looking at. So the impedance matters. So basically it's going to be like a AC circuit, not a DC circuit. So you need to know the dynamic dielectric behavior, and different molecules, they're going to have different polar. So when you put a field on it, the polarity of the molecule shifts, right? And that's kind of how it's storing energy. It's basically there's a relaxation time to that shifting of the polarity of the molecule, which is related to the glass transition, to the polymer, you know. So it's basically, you need to know a lot of information to plan this out. And the perfect one hasn't been found. And the other thing is he's looking at also there's a lot of inorganic materials that have better dielectric constants than polymers. So you can add in a nano filler, and then that's going to involve like the dispersion of it. And if you're talking about nanotubes or like carbon structures that have asymmetry, then you have to worry about the orientation of those things too. So there's a lot of parameter space to kind of look at that you're going to feed in. So somehow you have to collect all that data, then you have to put it into computer language, so ones and zeros. So whatever, and all the different things you have to convert to ones and zeros. So you have kind of a transfer function, right? So you can think of like a sigmoidal function is one function that can do that. So that's 1 over 1 plus e to the minus of the number that you're measuring. And then that thing will go through a sigmoid. So it's an on-off kind of function. It's got a little transition in the middle, but it's kind of on-off. Another one you'll see is this tan H function, which is almost the same thing as sigmoid. A sigmoid goes from 0 to 1, and a tan H goes from -1 to +1. Other than that, I know nothing about what a hyperbolic cosine or whatever are, but the tan H is the only one that they use. And it's basically a switch function. So it looks like a sigmoid, and it's centered around 0. So it's perfect kind of function for the switching operation. So you see, like they randomly say, we're going to take tan H of the dielectric constant times a constant. That's like, why did you do that? And that's going to be their weighting function. They're going to sum those up to get their decision. Like, in other words, it's nice because it's going to go -1 would be really bad and +1 would be really good. And and then they can sum those up. And if it comes out a negative number, this could be fractional if you're near the cutoff point, comes out to be a fractional number, then they can say that one's better than that one. So you need this kind of conversion function to do that. That's all kind of in this data collection thing, and then the fingerprinting, like it's mixed into this, right? So it depends what you're doing, how you go about doing this. So I'll show you some examples. I guess maybe the quiz will have a couple examples where people are doing this kind of stuff. So again, like it's not exactly science. Like you've thrown away any idea about you're going to model it, or you're going to understand it. That's all gone out, and all you're trying to do is get to the end, like a better dielectric without any kind of understanding, right? Or maybe some kind of understanding could fall out of this by accident, but understanding is not the point of it, right? So in that sense, it's anti-physics, right? Although here we are looking at it, but so anyway, the collecting the data. So I was talking with this guy Koopa at UDRI yesterday. He's like, "Oh no!" I was saying like we should put this into this proposal. And he's like, "No way, this isn't like something that we should be doing." Despite that, all the money is in it. And he said like, "I went to a conference on this, and like, it's not worth really going after." So I don't know. He's poor too, so it's like. In terms of research funding, so maybe why, it's like, so, or not desperate enough, I guess. So he's got kind of a secure position there. So anyway, so I always think that like the advantage of the US over Europe is that we're much more desperate. Like a US average university professor or whatever, average university student, I mean, everything is spelled out in Europe. It's just like boom, boom, boom. In the US, everyone is desperate. That's the difference. And that's why we make Microsoft and they don't. And it's not necessarily, in other words, if you look at the two groups, like who's happier might be a good way to judge it rather than who's richer, because I think we're generally pretty miserable. So at some point we should kind of look at it that way, like set a goal of everyone being happy. So, or not crazy or whatever. I mean, we have a lot more shootings, like the New York thing, right? So it's like that too. So it goes together. Of course, they had the thing in Berlin, or the guy drove the car into the Christmas market. It was like last year or something. So anyway, it happens. So we got all the data and this websites, and Mike was saying like the other day, like he's been doing this at Lyondell, and it's like, yeah, this is a thing. It has like 10,000 polymers in it, and you're trying to find the one that's got the right TG for your process, or like you want it for whatever pipe you're making. It can't sag, so it has to have the right whatever creep resistance. So, but you can't find exactly creep resistance in the data set, and you can't find, and the data you have is mostly like questionable too. So it's like from sources that are not, like you don't get to vet your sources. If it's coming from your lab and your company, you know that this guy John is like a slacker, and you know that whatever he did, you don't trust. But here you're just pulling stuff off the internet and it's random, right? So it's totally random if you can trust it or not. If you collect enough bad data and it agrees with itself, you say, well, I can kind of trust that, which is kind of the same way you dealt with John, because Sally and Jim came out with different answers. He's saying John's wrong, but John might be right, and Sally and Jim might be the ones that are messing up. So maybe they're taking the same drug or something. So who knows? Anyway, so there could be bias in it. So you have these sources, and they already exist, like to a large extent, but they also like way overpromise what they have. Like this polymer genome, materials genome is a classic example, funded by NSF. They dumped a bunch of money into it. They got a bunch of grad students. Like nobody wanted to do this, right? So they basically got the money, and the university takes 50% of the money to go take trips to the Caribbean. And this was literally like Stanford took 70% of the research money and literally was taking trips to the Caribbean for the administrators, they got in trouble for that.
Meanwhile, there's like, hey, grad student, like,
Right.
go test all
Yeah.
these samples and give us the data.
Yeah, so go collect, well, just go surf the internet and find every TG for every polymer and then put it into this computer program, right? Literally, this is what the materials genome is. Like no other faculty ever touched it. They kind of glanced at the web page, well, that looks pretty flashy, you know? So when you go to use this stuff, I mean, it isn't of use at all, really. I mean, but basically these sites do exist. NIST, on the other hand, their main prerogative, they were originally National Bureau of Standards, NBS, in the 60s, whatever. Then they became National Institute because they saw like NIH was an institute, got roughly 100 times the amount of money that they were getting, like a huge amount. If you go to NIH, it's this gigantic campus in Bethesda.
Like, can we just rename ourselves and get more money?
Yeah, I mean, you drive on, what is it, like Connecticut Avenue, and it's like just both sides and it's towers, right? That's NIH, and it goes on for like maybe 2 or 3 miles. NIST, on the other hand, is this little compound in Gaithersburg on 270, like outside DC. It's got good people at it, but it's this little teeny thing. You know? And they got a few brick buildings and a nuclear reactor. I mean, meanwhile, the entire Washington is expanded around it. And no one in that area knows there's a nuclear reactor there, where they do neutron scattering, right? So it's a small nuclear reactor, but still, you know, it's kind of dicey to put it in the middle of the city now. The city grew around it, but you know. Anyway, so NIST, their main prerogative is like find standards. And so this idea of like standardizing every polymer, they've been doing that since the 1940s. So they have like polyethylene standards, every kind of standard that you can think of, they already have. And then probably about 30 years ago, they started putting it into the web. So they have like in this web book, so they have an extensive array of information. If you go in this web book, you can find anything. They used to look in the chemical handbook, you know, and it's all there in like, and it's been vetted. Like all this information has been vetted by professional scientists that are high caliber. So, and they give you their impression of what the quality of the data is. It's in a format that you could potentially access with a computer program. So anyway, so that should be the place to get the data. Still, it's lacking. Like it doesn't have everything you need. So that's kind of a problem. There's other, like this thing's like quantum mechanic, the Polymer genome, that's the thing, the NSF funding thing. And there's like quantum mechanic simulation results kind of website where you can get quantum mechanical. So quantum mechanics is because you want to do, especially in dielectrics, you need to know what they call the density functional theory, right? Which is, it's really electron density. So it's like the Schrodinger equation. It's quantum mechanics. It's like this QM9 thing. So output of density functional theory is going to be QM9 web page information. And you need that to know kind of how the electrons are hopping when you have a dielectric, like how the motion of the electrons, what's the electron cloud look like, and how could it be polarized, and things like that. So this dielectric problems, and it seems like a lot of the things that this machine learning has been applied to have to do with like quantum mechanical stuff too. So, I mean, I found some things on polymer nanocomposites, but they aren't, even there, they talk about nanocomposites for electronic applications. So it seems to be that then this nanomine's another NSF funded quagmire thing about nanoparticles. So this polymer genome is just polymers, and then they were doing nanomaterials. So everyone said like, oh, you need a nanomine, and it's going to have all the information. And I think this started, so a lot of this started Northwestern at RPI in Albany, or in Troy, New York, right? And then kind of moved around the country, but I guess Duke has something to do with it. I think this Brinson is a student of Chandler, who is, I think, who was at RPI. So I think it links all back to RPI and then Northwestern, this business of it. All this data, whatever, you know. Anyway, so this thing isn't just one set of numbers you need to get, right? So this is a mapping from that paper, but basically if you're looking for band gap, whatever, electronic properties, you need to think about quantum mechanics, which is subatomic. And then you need to think about, well, if you're doing simulations, which these are both simulations, molecular dynamics and phase field is for interfaces. So names are kind of weird, like phase field actually has to do with interfaces. So you see electric breakdown, those are all interfacial properties. Then finally, if you get to bulk properties, so if you're mixing it and you have a compound, then you need to model how a nanotube is going to disperse when you mill it in a polymer, right? So the orientation of it matters a lot for conductivity. It's going to conduct down the tube. If they're all pointing the wrong way, it won't conduct, right? So basically, if you get to larger scale, and nanotubes can get into microns, and microns you need to use this kind of constitutive models, so basically non-thinking models. So you break up the material into a grid, and then you apply stress to it, and you see how things move in response to that. All these sections have their own software packages. Finite element is, so it gets kind of more expensive the higher up you go. Maybe it's because it's more useful. It's like these you kind of have to pay for the finite element programs. Quantum mechanics, they pay you to take it. You know, so it's like basically, maybe people think it's less useful, but basically you need the whole picture of the thing, right? So I mean, they're trying to get money off these things. But basically, the MD was done at Sandia, and basically the lamps, and you can just download it. It's like these are pretty simple, and phase field has similar packages for interfaces. So I say that, but you know, if you actually do this, it's going to take you a month to get into it, and then once you're into it, if you start doing this, it'll take over your life. So it's kind of like Buddhism or something. It starts out like there's no religion, and then you start doing it, and all of a sudden it's more religious than the other religion. This is kind of like that. It starts out like you're just toying around with this thing, you download it, and if you start doing it, it becomes the only thing you do. Yeah, so it's a little bit of an addictive like process, I think. So you should keep that in mind before you do it. You know, on the other hand, could be lucrative. Like the reason people keep doing it is because there's money in it, and it's seemingly easier to do than actually doing an experiment, right? I mean, you don't have to actually get your hands dirty, and you can just work at your computer. But if you realize, like, I mean, yeah, there's some work involved in getting up and going in and doing something, but basically, in the end, you understand more from going and doing something, and also you seem to actually achieve something, you know, whereas this never sure like what you got out is worth anything. You know, that's kind of a problem with it. So anyway, so this is this interface software. There's a bunch of them. Like again, like you can just download those. To get beyond like looking at the front page involves that you have to download a shell environment, and so you can't just like demo these. You can demo the results of them, but you can't demo, like you can demo the result of a molecular dynamics simulation, but you can't like demo in class, like how you go through the routine, because basically it's going to be a bunch of steps of downloading different components that run the software. It isn't exactly a software. It's a collection of scripts that run, and you end up doing a line scripting. You don't have like an interface that you're using. All right, so it's kind of like the terminal in a Mac. Like if you've never been to the terminal, this may not be the way to go for you, you know. But the terminal is like where you can control every itty bitty thing about your computer. You can do everything you can do with the menus, but you have to do it by typing in a line item. This is all like that. So this is just showing like how, just showing like that's a Schrodinger wave equation, and they're going to get like somehow the electronics at the interface is going to be spit out of this one of these softwares. So you can figure out how the interface breakdown works as a function of the molecular structure of the things in there. That's roughly the idea. So in polymers, in inorganics, in metals, you have like a band gap, right? So in polymers, you have this HOMO and LUMO, which is like a band gap, highest occupied orbital, lowest occupied orbital. there's a band gap between them that they don't call a band gap. And it's the same thing, like if it's a semiconductor, the band gap is small. It's like in a solar panel, the band gap matches the energy of sunlight coming in, and that makes electrons jump, and that's where you get your power from. Right. So same thing with this. Like you're going to have some kind of jumping between HOMO and LUMO and get and that band gap or whatever this thing's called matters and how the performance is. And you can predict that band gap using this density functional theory. That's the idea, or software that you download to do that. And then there's data sets for the dielectrics. This is just showing, I guess this is showing that in other words, this heats up. When electron flows through, it's going to make heat. So you need to model the thermal behavior of these things. This is just showing an example from a paper that they did that. This is dielectric breakdown. So you can see like it's conducting at some point, it's not conducting at the other. As you increase the field, there's this breakdown voltage. That depends, like if your use environment, what that is. You can spec that cutoff. So this is simulated. So you can simulate that for all different materials, find the range that you're interested in for breakdown, and then go back and say what material would give that to me. Like in other words, if you look at enough materials, if you simulate enough materials, you can kind of predict what the next one's going to be. So this is just the collecting the data part of it. It's basically this data set, step A of this. Then once you have that, then you have to do this fingerprinting. And again, that's going to be, so in terms of molecular structure, so each of these things people are making livings off, you know. It's like this thing, this SMILES thing. Like I heard a 1 hour invited lecture just on SMILES at the American Physical Society meeting, right? In a series of talks about machine learning that are all in, like usually a talk at APS is 10 minutes. So those are the contributed talks. So if you get invited and you get a 1 hour talk, that's got to be something kind of Nobel laureate type thing. Right? So anyway, 1 hour talk from the guy from MIT that invented the SMILES thing, which is basically just take any polymer structure and then write it into like ones and zeros code, so you can spit that into a computer. Then it can sort through it. It can categorize it into red, blue, green, or it can figure out like which one gave me this dielectric breakdown that I wanted, like wherever that is. And then it can spit out, it can just choose which one and then say randomly what ones and zeros would I say would work for this, just from the trend of the things, but not even knowing what ones and zeros mean. Right? The computer's just going to go like ones and zeros and say which one looks best. So, and then this thing A is a more traditional way to do this. So this is without any knowledge. This is called the group contribution method, which you may have heard of. But basically, there's carboxyl groups, there's thiol groups, there's ethers, there's whatever, aromatics. So you can break down organic molecules into their families, right? Or metal cage structures, like in the last homework where they have the orthogonal structure and this like metal cage, like chlorophyll and things. So basically, you can break down into these categories, and then those categories, you could say like my chemical has aromatics, it has ethers, it has carboxyls, it has some metal cage things. And then I can say like, I can just categorize in that sense, like this isn't doing that for you. This thing is just ones and zeros for where the carbons are. So anyway, there's different ways to go about this. Like this is a little bit thinking, and this is no thinking at all. Like that's the difference between these two. So maybe you need to use both. Like you might need to use more than one categorization technique. Then there's people make kind of quote unquote making money, meaning that like DARPA, some huge deep pocket government secret military funding agency is going to say, oh, we have all this SMILES code for everything on Earth. Then can you convert that into a computer graphic or something? So you can rotate the thing around. So that's what this RD kit does. So no one's buying this shareware, but they made money off it because it was like either DARPA just directly gave them money, or it's one of these startup company sham type things. You know, so the government the Congress said that all the research money was being wasted because they didn't understand what it was doing. So they said that something like 10% of all the research money the US spends has to go into startup businesses, right? Which is a huge amount of money, because including the Defense Department and the Department of Energy and the NIH and NSF, which is a small thing, right? And Commerce, which is NIST. So that 10% goes into a pot, and anybody with any kind of crazy idea just walks in and takes the money, right? So that something like our D kit could get, they do it in stage 1, stage 2, stage 3. So stage 1 would be like $200,000. Stage 2 would be like $5 million. Stage 3 would be like, stage 3 you're supposed to be commercializing, so you only get another like 500,000. Basically, if you do enough of these little RD kit things, pretty soon you're talking like real money. So there's companies, especially like if you go to Dayton, UDRI, and then there's a whole business park of just these kinds of companies going off the Air Force. Some of it's legitimate, but I'd say the vast majority. I was reviewing some of these for DOE, and it's like, it's something like, I forget what they were doing, new fast neutron detectors or something that is crazy, like, and I think it was funded for like 200,000. So you try to get 200,000 to do a research project. It's like pulling teeth. Like they're never going to give it to you. Maybe once in a while, But doing this, if you could put it into this framework of a business thing, anyway, it's kind of crazy. So 10% of all the money, of which they keep cutting the budget, has to go to this kind of thing, So anyway, not that I have a grudge, but So, and then there's different levels. So actually, so there's these simple fingerprints at one level, just the chemical information put into it, numbers. Then there's other, like this BIOVA is going to talk about like levels of structure. So it's going to categorize. So something like, almost like you could combine these two, like, obviously this is too simple. This one isn't digital enough. And this BIOVA is like saying, well, we start with the smiles, and then we have the other things like group contribution, and then you can make that into levels of structure for the thing, so you can kind of pile it up. Right? So that's a little bit obvious, but doing it, probably some kind of national funding thing. So the hierarchical fingerprints gonna include like data taking, right? So like some kind of data taking, some kind of binning of the data taking. Then these kind of digitizing of the chemical structures, put in quantum mechanical information. Let's see, this isn't quantum mechanical. QSPR is this whole process thing, and then the compounding information and orientation information. So you end up with this kind of complex. The fingerprint isn't just a smiles file. Like this QSAR is like try to be a holistic thing, right? So these are all the different spin-offs. Some commercial, meaning this 10% initiative thing from the government, meaning they aren't really commercial, And then freeware, meaning people said they just wanted to do that, or it was a thing from this government and they made it free after they realized they weren't going to make money, or whatever, so the free stuff is probably more important, but it addresses like all these things like this quantum mechanical, homo-lumo, thermodynamic, so you have to worry about hydrogen bonding and things, and then constitutional, that's whatever you mixed in if it's a compound, geometrics like the orientation, and then topological, I'm not sure what topological is, but so anyway, Quasar is like thinking about all those things at once, like hierarchical fingerprints. So, and then the orientation kind of, again, this is straight from that paper, basically physical numbers, shape. So if you use nanotubes, graphene, or you have just silicon particles, and then how are those oriented in space and distributed? So it's got to be like, do they clump up or do they not clump up? And do they clump up on different, so if it's a nanoparticle, it could clump up on the nanoscale and it could be dispersed. So you could have clumps that are dispersed, right? And then those dispersed clumps could form something that's clumped on a higher level, right? So these are going to be on multiple level scales over like 8 orders of magnitude in size, right up to like people size, or it could be even larger. It depends. So anyway, so this distribution parameter, none of these are really simple questions. Like the shape parameter, most things are like dust bunnies. So you make something that's narrow, it makes a dust bunny. They collect together. That thing isn't a rod, and it's not a sheet, and it's not a sphere. It's like a cloud kind of, right? So how do you, like the shape parameter could mean a lot of things, and some of those clouds could be stretched out, and some could be like oblate or something, or prolate, whatever. So anyway, so there's a lot to this as far as categorizing. It depends a lot on what you're looking at, right? And then this is the interface stuff. The shell parameters, like how the interface between the two things matters for it. So that all has to be categorized somehow. Part of the categorizing. So the scattering people always get into stuff. It's basically, you can take an image like this, you can Fourier transform it, and you can get a correlation function out of it. Or you can take a scattering measurement. So one of the papers I might use for the quiz has this kind of thing. So this chi, real space chi inverse space. So you take the scattering pattern, say k would be q, scattering vector, and then you take the ideal scattering and you take the deviation between. So you can have a chi, what do they call it, like your measurement minus the measurement squared, like a standard deviation. So chi is something like a standard deviation between what you want in inverse space and what you have in inverse space. So if that has peaks in it, it's a bad thing. Like you want it to be flat zero, right? So anyway, you can transform that thing. So people are doing this. How productive this is, I don't know. But basically, people are doing this basically because this scattering measurement, if you do it at a synchrotron, is 20 milliseconds. And you can literally do billions of these measurements in a week, right? And you can do it real time. Yeah, you can do it real time. So try to do that with a TEM, like you're not going to be able to, right? So, and you're looking at TEM size scale. In fact, you can get this Q thing to go up to like 5 orders of magnitude. So you can get optical, SEM, TEM, and then atomic scale, and get diffraction in the same measurement, right? So it's a lot of information, and it's set up for this machine learning stuff. Like if you can generate 1 billion data sets like that, then you have to have some kind of computer to figure out. And it's looking at different length scales and how they interact, right? So it's this kind of Fourier space thing. Could be legitimate, or it could be just the way people get jobs to do stuff, or it might work out into something, or they could be like sending them into the moon and they figured out how to make toothpaste tubes. So it could be the spin-off things from it. But anyway, so that's there too, the Fourier thing. That's going to fit into this fingerprinting thing, the first step of this thing. And then this is basically how people are like categorizing stuff. So there's a bicycle, and you break it into pieces. This is image analysis. So you're going to say, like, I can identify. It's like when they have the thing to test you to see if you're a person or a computer. And the computers are getting better, so they have to make those more difficult. But basically, is there a bridge in this picture? The computer can raster across and have roughly an idea what a bridge is. And it can, and there's different things that could be in the picture. So you can have this kind of levels or layers that you put it through. So is there a bridge? Is there a person? Is there a guy with a gun? Then you have a guy with a gun walking over a bridge, and that's the picture you want. So that's the idea. There's a bicycle finally, but you have to go through the pieces. So this is all image analysis, but like Mike said the other day, most of the stuff people are doing is like defect. Like you're running a production line, and you want to know when there's a defect in the thing. You want the image. You're taking a picture of the stuff that comes out. So you have, say, you're blowing garbage bags, which is what they do. So they have a camera on it, and the camera is like taking pictures all the time. 2 megabyte pictures, and it's throwing those into a computer, and it's searching for like a street or a block of something, because once that goes through, so then they blow it up into a thing. This is 3 stories high, right? And then it's going to crimp it into garbage bags someplace. So basically, if there's one flaw in that, the entire thing just collapses because it's blown up with air. So it's a balloon. It comes out as a tube, it blows it up like a balloon, and it's crimped at the top. So if it gets one defect in it, you need to know right away to shut the whole thing down, because in like 30 seconds, you've gone through like a couple 100 pounds of plastic, you know. So it's basically a lot of stuff flying through fast. So you need to know to quickly identify. So that's what why he's interested in this stuff. But and so image analysis is a big part of it, you know. So then once you do that, then there's this part of this machine learning is that kind of screening. Like you're going to try to do identification of different components. Part of seeing if it's meeting your property specifications. So these things are a little bit intermingled with each other. Right, like the decision tree is partly linked to this image analysis thing that's going to be categorized and get your fingerprint. So you can see like with the bicycle, you're going to have like, is there a wheel, is there a frame? Those are going to be different levels on this machine learning algorithm, right? It's going to feed the image in. First, it's going to get rid of it's going to clean up the edges, get rid of bright spots or something. You know, most of this was originally done with images, but it can be done with data also. So you get rid of the noise pattern, you find the baseline for whatever DSC curve you have, so you flatten it out so you can analyze it. And then you're going to end up with some sum of things. It needs to be like this tan H thing. Like there's got to be a yes, no. It can't be like the dielectric constant and the glass transition. One's a temperature, one's some other number. They have to all be on a scale of kind of 1 to 0 type thing. So you can use like a tan H, a delta function, and not delta, but like a sigmoidal function to do that. You're going to sum those all up. Then you're going to get a final decision number that's going to go from like 0 to 1. And then that's going to be like a soft decision, right? In other words, it's not going to be exactly yes or no. It's going to be that's better than that, or that somehow.
This is a dog. This is
Yeah.
a cat.
And this is kind of like, all right, so take a hyena, which is a dog cat, literally. So
It has to make a decision though.
yeah, is it a dog or is it a cat? Right. We go, you know, I used to take undergrads to Ethiopia, and then there's a place in Ethiopia where you can go and there's people that feed the wild hyenas, and they'll like climb up on your shoulder. So you can take like a hot dog or something, and the hyenas will climb up. I have videos of this. But anyway, they are dog cats. So not exactly as friendly as a dog, not exactly as dangerous as a cat, but somewhere in between. Dogs are more predictable, you know. I mean, you know, if you feed them, they're going to be okay. Cats, not so much. Like cats, actually, the guy that used to drive us around was in a lot of wars, and he said he hated cats, and he hated cats because he went into a place. The cats actually will eat their owners, like when they die. You know, so it's like that's why he hated cats. He went through the story. He saw that like his friends. So anyway, Ethiopia. Anyway, so yeah, we're kind of out of time. So basically, I think you get the gist of what's going on here. Hopefully the cat story won't hurt you. It did kind of hurt me. Like I grew up with cats, and like I never really thought about them the same way. Anyway, so you're searching for predictive, you're looking for areas where you want to be, and then your input parameters and how you could get there. So suggesting like what you could, so evolutionary would be like you go measure some more samples to put in, and then you can evolve, you can use this process to discriminate and then say where to go to suggest new samples. So it's different. The genetic algorithm has to do with that. Like you're basically trying to mutate your samples to get them to meet specifications that you want. These are like, they do these synthetic pictures of people now. These are computer generated. And again, these are not patentable. So you can make a person, you can take a lot of pictures of people and you can make a person, but that person you can't own. Like you can't own that photograph of that person because it's computer generated. So anyway, so you can do the same thing, like predict what you want. And then that's about it here. There's some statistics on analyzing, but it's not that important. So anyway, so I'll work up some maybe 2 papers probably, like because they're simple. Like the ones I have are really simple. So I'm not sure I can do a quiz on 1 paper on a subject. You know, hopefully it'll give you some feel for where it would actually be implemented. There's a link. Oh, there's a link on the webpage to one thing that my son works at NIST, and he said that this is like a good one. It's an example. He's doing machine learning stuff. So he said this perovskite thing is a good one. It's not polymers, but basically because perovskites are made from kind of a random mixture of metals and organics to make something like a solar panel, solar collector type thing. That was one of the uses for perovskites. Anyway, so they have a huge space of materials. So they raster, so paper, chemistry and materials, where they raster through all possible organic. You can see what they did. Yeah, and basically just try everything and then use a computer to optimize it. This is like NMR data. And then these are the crystals they got out that the computer told them to make, right? So they have better properties. So that's linked on the, under the developing homework 13, the perovskite thing. But all right, so it's an example of this.